We're going to start chapter 3, and it's on derivatives, right? So we're going to first be introduced to this concept of a derivative. You kind of sort of know about it. You don't know we haven't talked about the implications of it and all that stuff. But you don't even, without even knowing, you've learned how to find a derivative of a function. So let's get right down to it. Let's first talk about the definition of a derivative, and that is that the derivative of a function f with respect to the variable x, you always find the derivative with respect to a variable, is the function f prime. That's how we label it, f prime. With the accent mark means prime in math, you now know that. And the value of the derivative is this. Now, the right-hand side of this formula, you've seen it before, right? What was that? That used to be, what we used to call that was the slope of the tangent line at a given point, remember? Slope with an E. What we also called it was the instantaneous rate of change. And now, I've always told you rate of change and slope were synonymous. And now we're going to add a third concept to it, and that's the derivative. So, these three things have to be linked in your minds forever. Derivative is slope, and that's rate of change. So derivative is rate of change, derivative is slope, slope is derivative, slope is rate of change. These three things are interchangeable and synonymous, right? And you have to know it so well. Just like when somebody taps you on the shoulder and asks you, hey, what's your name? And you're like, it's Benny. In the same way, you should be like, hey, what's the derivative? Oh, it's the slope of the tangent line. Also the instantaneous rate of change. Like, that's how quick it's got to be. Okay? You might falter on like, what's the date? Fine. But the slope and the derivative, we're not going to falter on that. Okay. All right. Now, if the derivative exists, and we'll talk about when it does and when it doesn't. If the derivative exists, we say that if f prime exists, we say f has a derivative, or we say it is differentiable. All right? So being differentiable means it has a derivative. Hey, I'm going to ask you guys, for the sake of efficiency, to take a second and all please unmute yourselves so I feel like you're here with me, and make sure I could see your whole face on the screen. So like if you have to tilt your screen back and forth, that all I get to see are, you know, your eyes, nose, and your mouth, and that's all I have to sort of check in on you, right? So I want to be able to see you. Okay. A function that is differentiable at every point on its domain is a differentiable function. So just like we had said, if a function is continuous everywhere on its domain, we call it a continuous function. Same with differentiable functions. All right, notation. There are a couple of different ways to note derivative. One is f prime of x, just like this, and that's how it's read, f prime of x. Now, because f and y are interchangeable, when we say f prime of x, we can also say y prime. That's the same, right? Because f of x and y are the same. Now, there is also something else. Because the derivative, right, is slope, and because slope is when we were like little kids, we said that slope was the change in y with respect to the change in x, right? And then we also said it was, you know, like the rise over the run. So the change in the y with respect to the change in the x. Well, you know, like in science especially, change is written as delta, right? That triangle delta. So the change in y can be written as delta y over delta x, right? Hopefully this is not too new to you guys. But when we use the term delta y over delta x, delta could be anything from half a unit to, like, you know, 3 years, or, you know, like a whole chunk of time, and so on. In calculus, when we talk about change, remember how, like, we want the points to be super, super close to each other? So we're only like changing the x value by a very tiny amount. Well, the notation for tiny amount of delta is d. So instead of delta y over delta x, we say dy over dx, right? So those two mean the same. And because dy dx, it's the slope, it's also the derivative. So I can also say dy dx for the derivative of a function. Now, dy dx, they're not just two things on top of one another. That concept, d dx, is an operator in math. You know about a lot of operators. You know about these operators, right? These symbols in red mean something to you, but they might not mean anything to somebody from another planet. But they mean something very specific to you, because when you see these two numbers and with that funny little symbol in the middle, you know that's code for you to combine those numbers and add them, right? That is called an operator. It tells you to do something to the 3 and the 5. So ddx is also an operator. When I take ddx and I put it in front of some other quantity like f, I know that I'm being told to find the derivative of f. Do you see that? So ddx is this thing that comes together. It's an operator together. So in that sense, I can write df dx, meaning the derivative of f with respect to x. And then I can also write ddx of f of x. So ddx of f of x. And again, that operator next to f of x says to find the derivative. All right. So let's differentiate. That's your new vocabulary word. Differentiate means to find the derivative. They're synonymous. One has no special meaning over the other. Of f of x equals x cubed. All right, so finding the derivative is exactly what we've been doing this whole time. We're just going to find the slope. So now remember, like, we didn't know if you were supposed to put m or whatever when we were doing this. Now we know that what you're supposed to label it as is df dx. That's why I kind of ignored it when you would ask me, do we have to put m? I never gave you an answer really, because this is what we have to put in front of it. So df dx, which is also called f prime of x, you could use either of those, is the limit as h approaches 0 of f of x plus h minus f of x over h. And here we're finding the derivative using its definition. We're using the definition of the derivative. So f prime of x is the limit as h approaches 0. When we expand a plus b cubed, it's x cubed plus 3x squared h plus 3xh squared plus h cubed. That's something you can look up. Eventually you'll know. Some of you might already know over h. When I cancel everything that can cancel, all the h's, we should end up with the limit as h approaches 0, 3x squared plus 3xh plus h squared. Cool? So when I plug in h as 0, all these go away. I get that f prime of x is 3x squared. All right, questions? We haven't done anything new. We just called it f prime of x now. All right.
Can you go back for a second?
Yeah. So we also have an alternate definition of a derivative, right? Because you can see how, there are some unnecessary variables like h in that definition of the derivative, right? F of x plus h. Well, we can eliminate it, yes.
So is df or is like dx of f is not the same as f prime of x?
Yep.
Okay.
Yep.
Okay.
Okay. So how did we get the h into our definition in the first place back, over a year ago? We said that if I have a point x, and then if I go over a distance of h, and I have x plus h, then I get on the y-axis f of x and f of x plus h. And then what I said was I would bring the second point closer so that h would approach 0, right? And so I found the derivative, the definition of the derivative, by saying this. Well, the reason why I put the h in there is because I chose to put the h in there, but I could have defined it in a different way. Instead of calling my 2 points on the x-axis x and x plus h, all those are like 2 different ways of naming a point. I could have also called them a and x, right? As long as I have 2 unique names for the points, it doesn't matter what I call them. I could have called them like happy face and sad face, right? So when I have a and x, I now have f of a and f of x. So then what did I do? Then I said, in order to make the secant line into a tangent line, I gotta bring the second point x close to the first point a, right? Close to the first point here. So x has to approach a. So another way of writing that same thing is, now what does the slope look like? F of x minus f of a over x minus a, just like this. But when does that become a tangent line? When x gets super, super close to a. So that now is the alternate definition of a derivative. What it does is it eliminates h. And so now you're like, well, which one do we use? If you're not told which one to use, obviously it's your choice. Sometimes you'll just be tested on a specific one and you'll be told use that, then you have to use that. Zoe, question?
For the other one, why is it?
Oh, huh?
Like what h equals?
Yeah, h equal. I was already in my new derivative.
No, I mean, like, wouldn't it then be? Oh, never mind.
Okay, so let's use that definition to find f prime of 2 here, right? So when I
do we plug in?
Huh?
Which variable?
I'm going to tell you right now.
Is the number? Okay.
I'm going to tell you right now. So now when we have f prime of a is the point that you're looking for the derivative at. So here, when I need to find f prime of 2, 2 is my a, right? So a is equal to 2. And f of x is equal to root x minus 1. So here's what I say. F prime of a is f prime of 2, because a is 2. is equal to f of x, well, that's f of x, minus f of a. F of a is root 2 minus 1 over x minus a, which is x minus 2. Where's my limit? Because that's just a secant line. X approaches to 2. All right, so that now will be the limit. Yeah, question? No question? Minus 1 over x minus 2. All right, what now? Multiply by the conjugate. And I get limit x approaches 2, x minus 1 over x minus 2 root x minus 1 plus 1. Now here in the numerator, I'm going to get x minus 2. Those cancel. So I get that this is the limit as x approaches 2 of 1 over root x minus 1 plus 1. Now I put in the 2. So I get 1 over 1 plus 1 is 2. Okay? Is one...
Wait, so this,
Yeah, go ahead.
this really isn't any different. It's just you're using A instead of H.
Okay, you took the words out of my mouth. I was going to say, is one any different than the other? Not really. It's choice, right? It's choice. Thank you. Okay. So here we go. ddx of 3x squared when a is negative 1. Okay, now here's another bit of notation for you. What we want is the derivative of 3x squared. So you see how after the ddx, you can put like f of x, or you can actually put the whole function. We want to evaluate this when x equals negative 1. So what you do is you put a vertical bar and you say x equals negative 1. And again, that crazy little notation, that's agreed upon by math folk, that's the derivative of 3x squared at x equals negative 1. Okay?
Does it matter if it's A or X?
Huh?
Does it matter if it's A or X?
It does matter. It must be x because all of the variables in here now are x's. So this should also be an x. So, right.
A.
So a, so it's okay to write a in that question or in a sentence because you're saying find it at a point when that point is equal to negative 1. But now when you put it in the notation, there is one variable and that's x and nothing else shall exist. Max?
But there's nothing that says that x equals negative 1. It just says that a is negative 1. How can you assume that?
Right, but here, look, in the directions for that, it says use the definition of, which is this, right? The definition, like the formula has a's in there, and now part B follows from that. So like these directions go with each other.
Oh, okay.
Yeah, okay? Yeah.
Miss again?
Yep.
Isn't the difference between this function and the one with age is that you can't just start it with plugging in like the number or whatever, because then the denominator will just always equal 0.
Well, you
Like, you have to
still
work it, right?
well, you still have the number because it's still x minus a. Yeah, so whether it's h or x, yeah, there is one variable, right? Whatever the limit is approaching, that you're not allowed to put in until the very end. Yeah, for x.
Okay.
Okay, so here it's going to be f of x minus f of a. A is -1, so 3 times -1 squared is 3, over x minus -1. Limit, as x approaches -1, I'm going to factor out a 3 from the numerator and get x squared minus 1 over x plus 1. And you know we can factor that some more. 3x plus 1, x minus 1, all over x plus 1. So now I have the limit as x approaches to -1 of 3, x minus 1. Now I can plug in my -1. So eventually I get -6. So dd, so you know, all of that is equal to -6. Alrighty, so the whole point of this lesson is for you guys to really start to understand the relationship between a function and its derivative. So think about what the derivative is, right? So now I'm just gonna ask random people now, okay? Zachary, what is the derivative? What does the derivative stand for? Slope, right? Jessica, what else does the derivative stand for? Slope and starts with a rate of change. Slope and rate of change. So, in my mind, like it's funny, like just like, you know, like two things are like completely synonymous to you, right? So is like the derivative for me, right? So just like if you hear the word mom, or like if somebody calls your mom by her name, like to you it's the same. You don't differentiate. It's the same. It should be the same thing with derivative and slope. So let's talk about the relationship between the graphs of f prime and f. Okay, on a scale of 1 to 10, when it comes to questions on the AP test, on a scale of 1 to 10, this is like level 13 importance, right? Like, you gotta know this stuff. Okay, so we just said the derivative can be thought of as slope. So when we have a function, we can do a pretty good job of estimating what the derivative will look like. Okay, so take a look at here. It says to graph the derivative of the function whose graph is shown. So what we're going to do is we're going to graph the slope. Now, what I have here is on the left-hand side, a graph of a function y. And on the right-hand side, I'm going to graph, let's label that y prime. I'm going to graph y prime. So if derivative is just slope, I begin by finding slope. Do you see how my function y is divided into 1, 2, 3, 4 segments, right? Clearly, there are like 4 different segments here. What we're going to do is we're going to find the slopes of each of those segments. So for the first segment, just like algebra 1 style, right? Slope is rise over run. M is equal to 3. For the second segment, slope is 0. What about the third segment? What's the slope there?
-2.
-2. And what about the fourth one? 1. Okay, so now I'm just gonna graph that to the right. Okay, what you need to be careful of is this. On the interval from 0 to 1, the slope of this function is 3 constantly. It's a constant 3 in that interval. So I go to the right, and from 0 to 1, I'm going to graph a constant 3. You see how that looks? Now, to the left-hand side, I have to close the endpoint because I'm on a closed interval for the y, right? My domain for the y is 3 to 5. I'm sorry, my domain for like the function y is what I meant. I'm sorry, not 3, 0 to 5. It's closed, right? So at 0, I have a closed interval. I have to close the endpoint. Here, however, right, to the right of that segment, I have to do an open circle. All right? Now, my next slope is on the interval of 1 to 3. I have a slope of 0. Open circle, open circle. The circles have to be open in the middle, right, where one segment leaves and the other one starts, because right at x equals 1, I don't know what the slope is. There is an abrupt change, so I cannot define it on my slope graph, okay? So just remember, close the endpoints, leave the inner points open. And then my next slope is -2 from 3 to 4. And then it's 1. And I close the right endpoint. Okay? Usually students do pretty well with that. Just remember, close the 2 endpoints. Everything in the middle must be open. Ethan?
Can you not find like the rate of change at x equals 1?
No, that's section 2. You'll see that it's impossible.
Okay.
It's undefined. Yeah, that's section 2. Okay, here we have a different situation. Look at this point, right? If I draw the slope of the tangent line, that's what the tangent line looks like. And then you see how the tangent line keeps changing in slope? But that change here is happening not abruptly like the one before, but very, very gradually. This is a smooth transition in the slope, and that's something that we can graph a little bit differently. So what we're going to do here is we're going to estimate the slope in the graph to the right and draw y prime. What we're going to do is we're going to pick a couple of representative points. The first thing I want to do is here, like the beginning, I want to call that A. Okay, there's going to be some estimating involved. I'm going to draw the slope here. We're going to estimate, okay? And I'm going to call that slope there A prime. And I'm going to estimate, look at how steep that line is. I'm going to estimate that it's about a 4. Now, don't freak out because we're estimating, and you know, it's very clear, like when I'm grading stuff from you, you know, I understand that there is some estimating involved. Okay, so don't worry about that. Another point which is good to pick is a peak or a valley. So here, I'm going to call that B, and that's a horizontal tangent. So we're going to say it's about 0. Okay. I'm going to pick another point here at x equals 2. So that was x equals 1, x equals 2. I'm going to pick that point. And here, if you estimate a tangent, it looks like that's a, you know, that could be like a -1. Okay. This is a good point, a valley. That's about, you know, 2.5 maybe. Or the value, like x is 2.5. And then I'm going to call this C and this D. So D prime we're going to say is about 0. And then I'll pick another one here at E. And that looks like it could have the same slope as what we began with, right? So I'm going to make it about a 4. Okay. Now we're going to graph those points. We said the slope at A, which is at x equals 0, could have been about a 4. We said the slope at B, which is at x equals 1, is about a 0. C, we said the slope could be like a -1.
Wouldn't those points be open?
Huh?
The
No.
A and C, wouldn't they be open?
No, we made them open before because there was an abrupt change at those points. But now there is a continuous change. And then D, like that was about like 2.5. We said it could be 0 again. And then E was at x equals like 3.5, and we said it could be 4 again. So the slope went from 4 to 1, I'm sorry, to 0. But that happened gradually, right? So it decreased from 4 to 3 to 2 to 1 to 0. And the whole thing happened very, very smoothly and gradually. So I can connect those points like this. All right, and that's how the slope of that looks. Okay. What you can also see, right, is trends. Here the slope is about a 4, and then here the slope is a 0. So it's decreasing, right? And here my slope is decreasing. All right? Okay. Now, let's see if we can go backwards. Let's graph the function whose derivative is graphed below. So what I have here is y prime, and I want to graph y. All right, what have I been told here? Y prime is -1 to the right of 0. I'm sorry, to the left of 0. So m is -1, and then m is +3 after 0. Right? So in the region to the left of 0, I have to graph something with a constant slope of -1. What does that look like, guys?
Line.
It's a line that's decreasing. Okay? Here. Okay? The y values can be like, you can have it further up or further down, it doesn't matter. And then at that point, it switches to a slope of 3. So it looks like that. Okay? We're estimating. Again, that whole setup could have been moved up or down. We don't have information for that yet. Okay?
Wait, and you don't need to place any points on the second graph?
No. Just like here we didn't when it was constant slope. All right. So one-sided derivatives. We could use these same definitions to do one-sided derivatives, right? And to find the derivative either to the left or to the right of a point. So if I have a closed interval, right, and I'm going from A to B, if my function doesn't exist to the left of A, then I can only find the derivative to one side, and that's okay. And here too, it is possible to just find the derivative of one side. All right, so take a look at this. Look at f of x here. Do you see how when I'm at this point, and when I find the derivative on the left-hand side of 0, my derivative gives me a value of -1. But when I find the derivative immediately to the right of that, I get a slope of +1. Because the left and right-hand side derivatives don't have the same value, I say there is no derivative at x equals 0. Okay. All right, take a look at this one. If I begin to find the derivative as x approaches 0 from the left-hand side, I get that the derivative is 0. If I find the derivative as x approaches 0 from the right-hand side, I get that the derivative is equal to 0. Because at that point, the slope is the same immediately to the left and immediately to the right, I say that there is a derivative at x equals 0, and I also say the function is differentiable at x equals 0.
So, like,
Yeah.
is there a way to solve that first problem algebraically, or is it just looking at the graph?
Oh, there is. There is, because to the right, so f of x equals x, absolute value x, is actually a piecewise function. It's got a value of x, or negative x, when x is less than 0, and it's positive x when x is greater than or equal to 0. So you can very well do it. When you're looking at it from the left-hand side, you use that as f, and then from the right-hand side, you use that as f. There is very little that we can't do algebraically once you go to calculus. That's the beauty of it. Like, that's the beauty of it. Like, it's everything just explained and defined and like put in front of you. And they're like, yeah. I've told you guys that, like, Newton invented calculus in order to be able to explain and write down and express the laws of nature, the laws of physics. So everything, whether it's force, velocity, acceleration, which are all related anyway, gravitation, like whatever you can think of, it all boils down to this. And this is the reason why Newton sat down and created calculus, or like, he needed a way to express everything. So this is a way in which we can explain everything. Okay, so let's use one-sided limits to show that the function does not have a derivative at x equals 0. Okay. So here, I'm going to use the alternate definition. So I'm going to say the limit as, okay, so this is the limit of 0 plus h squared, right? This is what we were like, f of x plus h and so on at x equals 0 minus 0 squared over h as h approaches.
Definition was.
I mean, I'm using not the alternate one, but the one that I told you like right before the test, where we had f of x plus h, and then we're going to plug in a right at the beginning. So it's like f of a plus h and so on. So from the left-hand side, we're using x squared. And so this is h squared over h, which is 0. So this is from the left-hand side. And I'm going to call this f prime of y from the left-hand side. And then
Exist because it's 0 over 0?
No, it's not 0 over 0 because the h, they go away, so it's h, and then it's 0.
Oh, got it.
And then here it's f prime of y from the positive side. And I'm going to use 2x this time. And it's going to be 2 times 0 plus h minus 2 times 0 over h of, here I get 2h over h, which is 2. Okay, so because the derivative from the left-hand side does not equal the derivative from the right-hand side, right? Therefore, the function is not differentiable at x equals 0. So again, the point of this problem is not to say that the function is not differentiable. Like, we know that. I told you that. The point of this problem, when we get to AP Calc, it's the justification. Do you have proper form when you're justifying this or not? Okay? And when I say AP Calc, I don't mean AP Calc meaning like I'm teaching, like because we're learning for the test. When I say AP Calc, what I mean by that is the AP course in itself is the college level calculus course, right? So what you would be expected to do in a college level calculus course, you're now being expected to do here. Like, it's the same, whether you took it here or at like University of blah, 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 somewhere else. So the expectations are the same, right? And those are like real life actual math. So that's what I'm expecting of you, right? And so like that's everything. Okay, it's all proper notation. Okay, homework, when I've been looking over at homework, it's been very, you guys are taking a lot of shortcuts with your work, right? Not cool. You gotta show me things, like you gotta write things down, okay? And guess what? In upper level math, we actually like write down some sentences sometimes. Like we use words, not just symbols. And that's cool. It's okay, right? We got to do this too. Okay. Question.